Hello everyone, it's our pleasure to have Pedro here to share about his work on the discrete adiabatic quantum linear system solver. And basically he shows that it has lower constant factor than the randomized adiabatic solver. Yeah, Pedro will be able to tell us more about that, and Pedro, the floor is yours.
That's right. Thanks for the invitation, Ian. So yeah, we're going to talk about our latest results related with our solver, quantum linear system problem solvers. So I have done this with Dominic Berry from Macquarie University, Don Gunn from Maryland, University of Maryland, and Ryan Babush from Google. So like just to start, trying to answer the question of why do we care about this problem. So that's solving linear system problems in quantum computers is a base of a host of new quantum algorithms, from machine learning to the solutions of difference equations, could be ordinary, partial, or nonlinear as well. In particular, I'm more focusing the linear system problem in solutions of difference equations. So the idea that when you don't have an analytic solution, you come up some methods for discretization, like finite difference methods, and then you're going to end up with a large system of linear equations to solve. And then the hope is to apply these quantum solvers to give some speed ups, compare with the classical results. So let's go back to the problem. The basic problem for the solving linear system problems on quantum computers. So you need to solve AX equal B, to solve for X. In the quantum version, you need to prepare the vector state B. And here you can think that the way that encoded the elements of the amplitudes of your vector state B is that the amplitudes are given as the elements of the vector. And you hope to get the same for the vector states of solution X after some application of the inverse of A. That's the way that you encode the states, that you can get the exponential speed up in terms of the equations to solve. So then you have the exponential speed up in n here, but the drawback of this method that you have to deal with some global property of your vector state. So you cannot read out everything, otherwise you're gonna lose the speed ups that you got it from the quantum side. And then this was first proposed by HHL. So these results, groundbreaking results. And here I just showed the list of how the improvements was happening since the HHL. But most of the better improvements to remove the quadratic dependency and get the exponential advantage in the allowable error in the solution, epsilon here, was given by approach using the adiabatic quantum computation. And then I can just here citing the asymptotic optimal results that we got it from our last results that give the asymptotic better optimal scaling, which gives in terms of these two parameters of the complexity of this for solving linear system problems, which are the condition number of the matrix they're trying to solve and the allowable error in the solution. In our latest results, we show how to do that. We got to show the upper bound using our adiabatic theorems, the discrete version. But there are also results that not published yet that shows the lower bound for this problem in terms of these two parameters that I'm talking here. And because of that, our results is optimal. We also have the dependence of the sparsity, but we're not considering here for this point of view. So here's the outline of the presentation. I'm going to just quickly go for an overview of our latest results that we come up with the discrete adiabatic theorem that used to solve the quantum linear system problems. And then I'm going to show the general procedure to solve linear system problems using the adiabatic approach, and then to do how to do it in the discrete version. And then I'm going to go for the randomization method for quantum linear system problem beats the quantum algorithm method as a question mark. right? So that's related with the previous results that claimed to do that. And then I show how to do the comparison between how we have done the comparison between these two methods. And finally, I'm gonna go for the conclusions. So starting with the discrete adiabatic theorem is just a quick review. So what is the goal here? So the goal is that you have some unitaries. You have unitaries. One is related with adiabatic version. So the adiabatic version is the one that you constructed that have information about the subspace of interest. In general, you have some, you write some in terms of a projection. In this projection, gives you the a subspace of the possible eigenstates that were interested to be at the end. And the idea is to compare this adiabatic unitary with the actual unitary that are going to work, going to use it, and see how far you are for each other, right? And then you can write these unitaries in terms of the sequence of these W operators, which also are unitaries, and then you call it by the walk operators. So you have these previous results from DKS that shows the asymptotic, that show how the walk is asymptotically accurate for solving the problem. But they only give the information about in terms of the number of the asymptotic results in terms of the total number of steps that you should use it without any information regarding the gaps of the problem. So you know that if you wish to apply for some quantum algorithm, you need to have the information about the gap. So that's how you work with the adiabatic theorems, right? So the idea is to show how slow you should evolve your evolution, your evolution of your system according with the gap. And also important to see that to notice that here and talk about the different aspect of the theorem, because usually when you have the continuous version, you think about it, always have to think about it, the properties of the Hamiltonian. Here, not think about the properties of the Hamiltonian, but the properties of the unitary. So in the continuous version, you have to think about the gap of the that you have of the interest of the eigenstates who are interested. For the Hamiltonian point of view, also have to think about the first, the second derivatives of this Hamiltonian. And the unit in the discrete version, you don't think about the Hamiltonian, you think about straight away from the unitary point of view. And so just quickly how we solve this issue with the gap. So then we think that we remove this order scalings results they show it there for strict bounds. So then we have to start, for instance, for the restricted bounds for the walk operator. So here we have dw, that means the difference of the walk operator. And you come up with these functions in terms of parameter S of the evolution, and T is the total number of steps, the steps that you are using for the walk. And you come up with a more general way to do this, these bounds, the strict upper bounds, considered high orders of the difference of the walk operator. Here you can think about this as a finite difference of your unitary operator. So it's kind of approximation of the discrete approximation of your or discretization of your derivative of such operator. And here, in terms of the gap, you have to, again, here, as I said, you have to think about it. The gap, you have to think about it in everything in the unitary circle. So the eigenvalues are spread around this unitary circle. And the gap is now this arc distance between the set of eigenvalues that are of interest and the others that are not. And here, in particular, for instance, you are interested about the red one, so then you can have this arc distance of this with the reminder of the eigenvalues. And then the idea to construct this unit, I mean, this quantities to see to get these bounds is right in terms of this. You have to come up with the operator form of the projection now in the point of view of the unitary. And this projection, as you know, you can write in terms of the resolvent of the operator, but the resolvent is in terms of the Hamiltonian, but here is in terms of the walk operator. And then when you do this way to express the projection, you're gonna have the information about the gaps. So in our case, the arc distance here in the entire circle. And then you have in our approach, considering like high orders of this, the multiple, how you call it here, this multi-step gap. So you have also the gaps for considering when you go for one difference of the walk or second difference of the walk. So the idea that the eigenvalues are spreading around the unitary circle, and you always consider the one that the worst, so the one that the closest to one in our analysis. So in our analysis, we're going to have the appearance of these different values of the gaps that comes from the results of when you have the first and second and so on difference of the walk operators. And then we start to see, for instance, this quantity here shows already the dependence of the gap in terms when you take the difference of the projection. So the difference of projection, when you write in terms of the resultant of the walk, it's going to appear the difference of the walk operator. And then when appear the difference of the walk operator, you're gonna see the gap one rather than gap zero. The gap zero is when you don't apply any difference. And the constant now, the functions now is both functions C1 because it's related with the walk dk1 here. So the difference d for which k equal 1. So that's start to appear these constant factors because we're doing some approximations and etc. And we end up with this. I'm showing this. I mean, a less tight version of our discrete adiabatic theorem with several approximations. Use it to get it, but it's nicer. A better way to present that because it's a nice way to compare with our results with the continuous version of the adiabatic theorem. For instance, here you see that these quantities are quite related. You see that the ratios is the same kind of ratios appearing. So how they're so in the continuous version we have this the dependence of the derivatives of the Hamiltonian, and the derivatives of Hamiltonian are related with our function C1s, right? So C1s are appearing for the difference of the walk. You also see the boundaries are the same. So we have it started from 0 to S, the same quantities related. And you also have the replacement of the integral or the continuous version by the sums, which we respect for the discretization form. So that's a nice way to see the similarities about it is the discretization of that. Okay, so given that you have already a better understanding about how this discrete adiabatic works, general picture, how you apply the adiabatic approach to solve quantum linear system problems. So basically the idea here is that you have two Hamiltonians, H0, H1, and you have H1, one of the eigenstates of H1 encodes the solution of your linear system problem. H0 is given by this projection QB that I call it, where this is related with the vector state B of your AX equal B, right? And the idea that is, this H0 is easy to prepare. And then the idea is to interpolate between these two Hamiltonians by a given eigenpath, following with interpolation by some schedule function, right? It could be in general just linear scheduling, but you can be more. You can think about other ways to improve the performance of their to go during the path, right? So to go in the most efficient way interpolate between these two Hamiltonians, and by having the properties, because H1 is already given in terms of the matrix A, and also the H not have information about the linear system problem, you can derive the gaps of your Hamiltonian, the time-dependent Hamiltonian, in terms of the schedule function that you introduce it artificially, and the condition number of the matrix that appears when you do this the analysis of the gap of the H of this constructed Hamiltonians, the interpolated Hamiltonian. And then one way there are several choices to do it, how to choose the schedule. But the idea to choose a good schedule is that we would like to slow down the evolution as the gap gets small, right? So the smaller the gap is, the idea is to evolve slower. So as you see here, the rate of the schedule function should decrease as I have the small gap. And here we have this version that's already proposed previously that shows in terms of the power of P, and we can choose this power between the values 1 and 2, not included 1, which cannot be included 1. But it's several options for a choice for schedules. And this is one of them. And then if you solve that, you see that they schedule the dependence in terms of the condition number of your matrix, the power P, and the parameter of S of the evolution. So this is the continuous version. So if you want to apply, that's how people usually apply. So you can plug this, you have the information about the Hamiltonian, you see the gaps, and you can derive some order scaling of using the adiabatic theorem, how slow you should evolve your Hamiltonian, time-dependent Hamiltonian, to get a desired solution, the desired solution. But if you do that in the continuous version, you have to use the Dyson series kind of approach. And this is going to have some overheads in terms, going to give extra factors there. In particular, you're going to go from a logarithm more a near linear dependence of the parameter of the condition number. And then using the discrete version, again, we don't have to think about the Hamiltonian, the eigenvalues of the Hamiltonian explicitly. So you have to write a way to construct a unitary and get the properties of a unitary. So you have to find the gaps of the unitary in terms of unitary circle. And the easiest way to do that is using this cubitization version. Why is that? Because the cubitization version has here in the end gives the information about is a unitary of the arcsign of the Hamiltonian, and the arcsign of Hamiltonian. So if you know already the information about the eigenvalues of the Hamiltonian, you straight away want to know the information about the eigenvalues in terms of unitary circle and also the gap. So then you can plug this information in your discrete adiabatic theorem, and to get the bounds that you needed to analyze the problem. And that's the cubitization is just the way to construct the cubitization is quite simple. It's just like a small modification from the blocking coding version of some matrix. So in particular, this is the blocking coding of our Hamiltonian, time-dependent Hamiltonian. But rather than do the projection on the state 0, project on zeros on the ancillary qubits that use it to code that, you do the reflection on the ancillary qubits, and that's the way to construct the quantum walk operator here. Okay, so in our previous results, so we show it how to construct this discrete adiabatic theorem, and then we just plug the information about the properties. I mean, the basic information about the problem, which in terms you can rewrite that in terms of the condition number of the matrix, and because you have the information about the gap, then the gap is in terms of the condition number and the total number of steps and etc. And you can just plug there the results, and this is results that show this. These results are derived using the first the discrete adiabatic theorem that I showed in the previous slides. But the important thing here that's nice that this allows us to show that the dependence of the problem is linear in kappa. So the idea that if you have some fixed error of this for our approximation solution on the left side, you see that the number of steps increase linearly with the condition number. And yeah, with the downside effect that you have really large constant factors that comes from the several approximations that you have to use it in our derivation of our discrete adiabatic theorem. And also tested that I have a more tight version from our discrete adiabatic theorems that apply less approximations, and you could reduce 9 times better in terms of the constant factor, but it's still large. And then you open the question. I mean, this is open the large constant factor that left the space to some wrong claims about the efficiency of this method, because you know that asymptotically accurate, these constant factors just give a half estimation about how many steps you should apply for matrix with specific condition numbers. But you never apply any instance of the matrix instance to of the solver.
Sorry, Pedro, I have a question over here. Like, why do you specifically choose P equal to 1.5 though? Like, any kind of intuitive reasons behind
Oh
this?
yeah, that's also, yeah. We choose it. We could show actually 1.5 was give the best results in terms of constant factors. That was the one that with the best performance. But it's like it just could be, you could find actually other that could provide us a better constant factor than that. And actually in practice, we use another one. When you do the numeric simulations for the practical, I mean, for instance of the matrix, we use it actually P equal 1.4 rather than 1.5. But it's like,
Any specific guideline to choose P though? Because it seems that it's just a hyperparameter that we choose from,
yeah,
and also you kind of choose it based on the constant, right? You want the constant to be as low as possible, so you
yeah, that's
choose,
right. Yeah, so
yeah.
there's a even less tight term that you have that's in terms of in the paper in terms of P, and then you can see what is going to be the P that's going to minimize your upper bounds, right? The minimum upper bound in this approximation. But yeah, there's no like, yeah, I mean, if you look at how you look at the scheduling, right? You can also think about it. Yeah, the idea is to minimize the rate, right? So as the gap increase, so the power of P. So then, yeah, so then you have to think it, what is going to be the best trade-off of this, right?
Right. And
There's no
this,
there's no rigorous here so far, but you could find something.
I see. So it's kind of like highly correlated with the gap and therefore the Hamiltonians that you consider and stuff like that. So
That's right.
this
That's right.
have to be chosen in terms of numerics, this has to be chosen in a kind of like a case by case basis, right? Yeah. So there's no uniform just like in machine learning, we just choose the hyperparameters based on our
That's right.
problem.
There's a hyperparameter that we could
Right.
tune. But in practice, what you find that once you find a good one for a particular case, it's going to behave a good for all instance problems.
Ah, okay.
So
Mhm.
we fix it when we fix one particular choice of P, or practical for in the numerics that we have done, we fix with this P for all cases. So, and that's pretty much that.
Okay, yeah, thanks.
And okay, so then talk about the randomization method for quantum simple problem. This is the quantum walk method question mark. So then we have the randomization method for quantum problem. You have a worst asymptotic behavior in terms of the parameters of the complex of the parameters of the complexity for the linear system problem. And sorry, here's a mistake here. There is also a logarithmic in epsilon. Okay, sorry for that. Says it's log kappa over epsilon. So this is a typo here. And in this method that we're going to show here, that's here in the giving the results here on the bottom of this slide, is a method to improve on some results, PRL results that I show in the table in the beginning. And so the idea is quite the same. So it's basically inspired by the adiabatic quantum computation. We also have the interpolation between, again, the same Hamiltonians, H0 and H1. But here you have to be careful because you don't interpolate the parameter v here of that are for the time dependent Hamiltonian doesn't go between 0 and 1. Here you have to find VA and VB such that you construct the FVA equals 0 and FBA equal 1. And typically we want to find these parameters. These are in terms of the condition number as well, how you choose it for the scheduling, etc. And the idea is that in the results they show up in using this randomization method, which have this evolution, this time evolution operator, this sequence of exponential of these Hamiltonians with different values of v's interpolated between VA and VB, how we choose here. And also is missing, again, sorry for that, is missing the subscript here, J, in the interpolation. And then we go, the idea that these T's are independent random variables following this probability distribution. And delta here is the gap as well, so it depends on the gap. So we're gonna select this, the values of these T's in the way that we try to minimize the average of the total time. And using this approach, they show a much better, tighter upper bounds for solving quantum system problem using the randomizer that we show it. So this table, this plot is coming from these results. And that shows, for instance, that here the darkest green area here between these condition numbers from 100 and 1000, that the results could do better despite to have asymptotic worse complexity scaling the complexity. They could do better because we have this much better constant factors, order of 8.1 times improvement over our results. And again, they haven't tested any instance of the problem the same as we didn't. The same as we also didn't in our previous results. And then, okay, now how you do it. So how we have done in these results. So we tested these methods both, and which kind of matrix we work with. So we work it in a specific case only with positive definite and emission matrix A, and only with the case no emission matrix in general. The no emission is more complicated because you have to enlarge the space to make that emission, etc. So you have to increase the number of qubits used. And then we go, you test it from matrix 4x4, 8x8, and 16x16, and with the condition numbers from 10 to 50, and for each specification of this matrix, like for instance, the matrix 8x8, condition number 10, we tested 100 instances for each case. So we test for each particular case, we tested 100 instances. So 100 for 10, condition number 10, and so on, 20, 30, and so on. And we have used the same instance problems in both cases. Okay. And also what you did for the quantum method, the quantum welcome method. So then you have the circuit implementation for both cases, or the circuit diagram for the positive definite, which is new, so we didn't have our previous results. So then we show how to do it. And the idea is that you have some target error. So delta is the target error that you wanna, which is the target error between the actual solution and the ideal solution. And the idea is that we apply the circuit of the quantum, use the circuit to encode the blocking code, the qubitization of the walk, and you start to apply from the scheduling the power P 1.4 that I have written here, and you evolve considering the interpolation between the scheduling function, it is already inside this circuit, from S0 to 1, using different amount of total time of steps. And then we start with a really small number, you start to increase until you get the desired target. And why 0.2? We show that because our results is in general for when you apply these methods for using adiabatic approach, you use the filtering at the end to be sure that you are in the right eigenstate at the end. You have to filter out the other eigenstates that are not interested. And you found out that this is the best trade-off to use it because you have to apply both. You have to apply the quantum alchemy method in the beginning, the filter at the end. And the filter, you also think about the walk steps to how many walk steps you need, time steps of the walk steps to do the filtering. And actually, the worst complexity comes from the filtering part, which is kappa times the logarithm 1 over epsilon. And sorry, yeah, kappa 1 over epsilon. And that's in opposed with just kappa here. So actually, so then you have to always to look at to the best trade-off. So that's where the 0.12 was for us that we found out. We showed in the paper how derived these results. Then that's the reason that we use it. And on the other hand, you have the use of the randomization method, but then you use the optimal probability distribution rather than the one that they use it. It's a bit light better. And remember this delta, small delta here is the gap. And the idea is that, as I said, these values T are randomly selected, chosen according with this probability distribution that you apply. That comes from previous results that I was given here, the bottom as well, is about the one of the optimization paper. This is for optimization paper. And for each instance, for this case, in the randomization method, you have to run it 200 times for each instance. And then we save it, we record the average result that gave us the minimal time, because I get to minimize the total time here to get the target, the desired target for the solution. So here you apply the time evolution of this operator rather than do some blocking code inversion, which is going to be more costly. So, and then we expect actually to get even worse behavior if you do the blocking coding for that in comparison with the blocking or recubitization. So that's the way that you did it. So it take this average of the minimal time to get the target in the randomization method and the total time to get it, walk steps to get it, the desired target state for the cubitization, for the quantum walk method for each instance. Okay, so here's our results. So I'm gonna just show here the case by the matrix 16 by 16. And the left side here have the positive definite case in the emission. No, sorry, the left side is the no emission case, the more complicated case, and the right side you have the most simple, the simplest case with the positive definite emission case. You see that this you have also these error bars here that consider the quartiles that we have of the problem, and that's you see that actually our behavior the performance of our results was even better in the no emission case, and that is important to mention that here in all cases that was tested, there was one single instance of the problem that we tested, the randomization method could do better. More than that, if you for a particular property of the matrix, so imagine that I have a matrix 16 by 16 with a condition number equal 20, and I have this 100 instance. If I select the best results that you have for the randomization method for over this 100 instance, compare with the worst of our quantum method, our worst still win. Okay, and this shows by there is no overlaps between the error bar here. This large error bars comes from difference Yeah, different characters for each instance of the matrix. And so yeah, in the worst case, I mean, so you can say that our method is one order magnitude more efficient than randomized approach. But remember that we are considered the worst case scenarios that you got it, which was the simplest case with the no remission, positive definite remission case. And you also not have done, you did the time evolution of the randomization method, how to do some blocking code inversion. Would be even costly. You're going to have some overheads for that computation for that side. And our constant factor, we went from value that was 2,300 to 1.56 in practice that we got it for these practical results.
So I have a questions over
Yeah.
here. Yeah. So have you ever tried to reduce the condition number? Because it seems like they will intercept somewhere for small condition number, right? So at least for small condition number, these two methods are comparable. Am I correct to say that?
Go even smaller than 10 or something?
Less than 10. Can you like go less than 10 for the condition
Yeah,
number?
yes, it's quite, I mean,
Yeah, and then like, they will eventually intercept, especially for the second case. They will like intercept kind of around maybe 5 for the condition number.
yeah, we could go and we didn't check it actually for these particular values because
Mm-hmm.
you are more interested to go the behavior has increased because that complexity increase has the condition number increase. So
Mm-hmm.
that's we expect to see how our approach gonna behave better.
Right.
And and we're still in the range of the darkest green area of the results. They claim it, they do better, 8 times better. And
Mm-hmm.
there they look at the actually from, I think they start from 100, something like that. And
Right.
yeah, then you still here even, you went even as lower than that, smaller than that. And then you show it that
I
we
see.
are much better.
Okay.
Yeah, but eventually we can compare and yeah.
No, as in like this. Do you know what is the typical range of condition number for the real problem that we want to solve? Like, what is the condition number of the of the matrices for the real problem will behave? Like, is it in this range that you consider
Oh,
like
yes.
10?
Okay, that's a good question. So, for instance, we are most of interesting in for linear system problems, right? In linear system problems, when you have some discretization, you have this type of triangular matrix in general, but you have depends of how order of the accuracy you're gonna deal with. But in general, the condition number increased according with the dimension of the matrix.
Mm-hmm.
So you hope to get really large condition numbers if you want to solve want to have a high precision values from your discretization to approximate the well resolution. So you actually expect to have larger and larger values for the condition numbers
Uh,
as you discretize, how you increase the number of points in the mesh,
mm,
right? So that's how you, so the condition number, because the structure of the matrix is pretty much the same, but what as you increase the dimension, you're going to increase the condition number.
right. I see. So like for larger dimensions matrices, then your algorithm even like win even more, right? Because like based on the extrapolations, the rate of increase for your algorithms much lesser compared to the randomization methods.
That's right. That's right.
Yeah. Okay. Got it.
Okay, then I come up with the conclusions of this presentation. So another nice thing that we show it here is the verification of the linear growth of the walk steps in the condition number, as you theoretically prove it in a previous result. So we theoretically prove using the adiabatic theorems, but then in practice you see this nice linear behavior uh, that that you just show it that you couldn't just proved theoretically previously. And then again, our results is asymptotically the fastest possible quantum algorithm for linear system problems in terms of this kappa, these parameters of the complexity. But now you also show that also the best results for practical cases, in practice for practical cases, until maybe someone finds something would be a specific range of condition numbers would be better. And also have this new constant factor derived that's about 1,500 times smaller than the that we found previously. And also have this it's not written here, but also have this way to look at more carefully the analysis between the filtering in the walk steps, the way to do this trade-off. And also you have now a nicer way. I mean, also have the circuit implementation for the positive definite case that we didn't show it before. And then we do that in practice. You tested this matrix. So that's all that I have to say for today.
I see. Yeah, thanks, Pedro, for the very detailed talks. And yeah, I found the comparisons between algorithm, especially for the practical case, pretty insightful. That yeah, because I don't think many people go and compare for the practical case. They just throw scaling on you and then say, oh, we have a better scaling and stuff like that.
That's right. That's right.
So for the audience, if you have any questions, please feel free to unmute yourself or type the question in the chat. In the meantime, I think I could ask some question over here. For your last point, right? Do you because from your numerics, we know that actually the constant should be much smaller. Do you have any ideas of how to show analytically for a smaller constant? Because
Yeah,
now you
that's we're still doing the same question actually. We're thinking ways to try to answer that. Because it's quite difficult to get these upper bounds. So like when you derive this discrete adiabatic theorem is a kind of complicated expressions that you have to deal with.
yeah, I could see that from the result it's showing.
Yeah, and then I'm pretty sure that we can find a way to get some better. There are a lot of scope for improvements there in approximations. I'm pretty sure that. But yeah, I mean, you only have to maybe stop and take work a bit more on that and to find better ways to get these improvements. I mean, better avoid to do some maybe too much loose bounds that we use it. Maybe have to rethink the problem from the beginning in terms of which was if it was or not ideal. You always can find some space to do a bit of improvement in the bounds in the approximations. You have to just spend time then and think more carefully about it. That's
Right.
I don't have any answer now.
Okay. And is your algorithm hard to implement as in I kind of scan through it, but I'm not sure how to code it by myself. So is it hard to kind of do the codings and stuff for your algorithms?
In the way that you have done, I mean, yeah, it's a bit. I mean, you have this circuit, but you have I mean, for each part you have to think it. Or for instance, you have the blocking code of the matrix A there inside, and you have to think a best way for you to do this blocking code of A. I think would be one problematic part. And there we, for instance, I use the method of the singular value decomposition that you can is really straightforward. And you also have to be careful about how you are applying the reflection operators, which are the ancillas. So this is actually discussed in the paper in the appendix. So here, for instance, the circuit, you have you have to reflect. For instance, you have to reflect in terms of the A1 and A2, and not in terms of psi. Is not psi. Is not the ancilla. And AH, because AH and psi, they are the part of the Hamiltonian, right? So that's gonna give you the Hamiltonian. this ancilla comes from the ancilla to construct the Hamiltonian that you have there. So you don't have you don't have flexion on that. That's a really important thing that I have to be aware.
Right.
This part.
Yeah, the reason why I ask is because like recently I have a work also, but on the Kubo side. So basically we just like borrow some intuition from physics. Like people have kind of like tried to use so-called like cool like landscape optimization landscape or landscape approximations of the low energy of some Hamiltonians, and then we just like map it to solve some Kubo problem that require us to solve some system of linear equations. What we did was just like did it rationally, and then in our paper we just mentioned that we can did it with HHL. Yeah, it will be very interesting to kind of see how your methods would help in those kind of problem. Yeah, that's why I come a bit interested
Oh,
on
okay.
to solve that efficiently, eventually using like fault tolerant quantum computers. Yeah.
Oh, okay. Okay. Yeah. I mean, I mean, for this particular type of implementation, we didn't think carefully. I mean, once you have the circuit diagram, we can find, right, some decomposition, interesting decomposition according with your gate set available. You have to be just analyze case by case, right?
I see. And over here, you didn't consider any properties of the matrix other than the positive semi-definite and positive definites and Hermitians and non-Hermitians, right? Because like for us, like we are considering like Ising models plus some kind of perturbations. So there are some structures in Hamiltonian that we could potentially exploit. I guess like this would
Sorry, are you saying about the important properties of the matrix A?
yeah, because like for okay, so typically for matrix A, right? And for Kubos, we will convert into the Ising models, right?
Yeah, yeah,
Yeah. And then it's like basically for Ising model, we have like Z and ZZ and something like that.
yeah.
This certainly have some structures in the matrices, right? And could we use this kind of structures to reduce at least the depth of the circuit? Because like at least for some specific, for instance, for example, Kubo, you consider a very specific type of Hamiltonians, right? Instead of
Yeah.
just arbitrary randomized Hamiltonians. Um, and I believe this could be utilized to reduce the depth or even runtime complexities of your algorithm. I'm not sure. Yeah, just some random.
Sorry, but I mean, which part could you think could reduce could
Yeah, for
help?
example, like for okay, we want to solve for Kubo problem, right? Then we will have a like matrix A, and then we encode in the Ising Hamiltonian, right?
Yeah,
And
yeah, yeah,
now for Ising Hamiltonian, we will have Z and ZZ
yeah, yeah,
based. Yeah, this is kind of a structure that we are looking for, right? It's not like random sum of Paulis, right? So we
yeah,
have the
yeah.
specific sums of Paulis, and this is kind of structure that we can utilize because like we know it's like for Ising Hamiltonian, there's symmetry. If like up, like all the ups will have same energy if all the downs, if I'm not mistaken. So there's some symmetry that you can
Oh, okay,
utilize.
okay, okay. No, I think now we're getting your point. So we are thinking about now to apply our discrete adiabatic theorem, right?
Yeah. Just like
Okay, okay.
general framework, but
Yeah, yeah,
and
yeah, yeah,
then
yeah.
for
Yes.
arbitrary matrices, right? But now I guess in general we want to kind of focus on a specific problem instance, and one of them will be Kubo. And for Kubo, we will have some structure that we can exploit, and whether we can use these kind of structures to reduce the complexities of the algorithms.
Okay,
Yeah,
okay,
this
yeah. Yeah. I think I I might follow your questions. I mean, you are thinking about the how you are think about the optimization optimization methods, right? Combinatorial optimization methods,
yeah,
right?
yeah, 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 yeah.
Yeah, okay.
Because
Yeah.
I have something like optimizations, and then I could encode that as a system of linear equations. Then now I could use your method to solve it, right? Yeah.
Oh,
So
you are
that's
thinking about to solve a linear system problem for the optimization. I was thinking
yeah,
to solve the time evolution using the adiabatic approach that's how you do it. One approach to do it is using the
yeah,
uh,
quantum annealer, right? Yeah, it's just like the typical quantum annihilers to kind of like do the time evolutions of
Yes,
the like yeah.
but you could also apply the discrete adiabatic version for,
Yeah.
yeah, and then the question would be more about the gaps of this problem to encode that.
Mm-hmm.
And you use the cubitization version. You also have
Okay.
a way to do the totalization. That's the results we're gonna come is about to come. Because here we show the prescription to map from the eigenvalues information that you have from the Hamiltonian to the unitary walk, the walk
Right.
unitary. And also going to do the same thing for the first order trotter method, which you
I
also
see.
to be plugged in the discrete adiabatic theorem other than the continuous version.
Mm.
That
Okay.
could be used for this kind of using this for solve optimization methods through adiabatic evolution, right? So that's the idea.
Right. Okay.
But I mean, for
Yeah.
linear problems, I to solve linear system problems for optimization, I'm not familiar.
Okay. Yeah. And it's fine. I think I could go and think about it. You just some of our recent work that could be interesting to apply with your algorithms.
Okay.
Yeah. Okay. Yeah. Yeah. Perhaps we can end the seminar now. And yeah, thanks very much for your time. I kind of gained a lot from your talk, and at least now kind of have an intuition of how to apply your method to solve whatever like linear system that I want to solve. Yeah.
Okay.
Okay. Yeah.
Other question you come up with, let me know.
Yeah. Okay. Yep. Thanks. Yep. See you then.
Bye bye.
Bye bye.